So in this video, we are going to start to talk about something called concavity and inflection points. So let's take a look at this opening example here on the right, where we can see that we have a location of a horizontal tangent line. So the first thing I want you to observe is that there is a horizontal tangent line. Oops. So there is a horizontal tangent line at x equals c. All right, so this means we have a location where f prime is equal to 0, but this is not a location of a local min or max. So it's not the location of an extrema. So we have a situation where f prime is equal to 0, f prime at c is equal to 0, but it's definitely, excuse me, not a min or a max. So we can kind of see this like shape change, but it definitely isn't changing from increasing to decreasing or vice versa. So let's kind of focus on what's happening with the derivative as we are both approaching C, and then we'll look at what happens kind of after C. So let's first take a look at if I was to maybe draw in some slopes of tangent lines, or what I want you to think about is what is happening to the derivative. So think about the slopes of those tangent lines I'm drawing in here, attempting to draw in, as I get closer and closer to C. Well, those slopes are decreasing. They are getting less and less steep, and they are positive, so they are decreasing. So the first thing I want you to observe here is that the slopes of the tangent lines, f prime, f prime is decreasing before, kind of as we approach x equals c. And then after, kind of as we're leaving, I guess you could say it that way, x equals c. So again, let's think about, and it's a little hard to kind of draw these in here, but think about what is happening to the slopes of our tangent lines as we are moving away from C. Well, now they're getting more steep. They're positive. They are increasing. So the slopes of the tangent lines, in other words, f prime, is increasing as we are leaving C. So those are increasing. So this is one way to actually define this notion of concavity. So where the slope, or f prime, is increasing, this is actually a definition, not the definition that your book uses as much, but one that we want to be mindful of. This is a definition of a region being concave up. If f prime is increasing, we're concave up. And if f prime is decreasing, this is a definition for what it means for the shape of that graph to be described as concave down. Again, not the definition that this book uses, but a really common definition for concavity. Sorry, I lost my image there. Let's get back. All right. No, I must have hit something there. My apologies. Okay, now, so what definition then does your book use? Okay, your book, if you kind of think back as we were drawing in those tangent lines, or maybe even looking down below here, when the tangent lines are above the curve, then that is going to be when the graph is concave down. If when you draw in the tangent lines, if they lie below the curve, then that is a definition for concave up. So kind of a different way to define concavity, or maybe not different to you, you've never really seen a definition for it, but slightly different than maybe what you could potentially see if you were looking maybe in a different textbook. So concave down, where the tangent lines are below, and the tangent lines are above, the curve is below. And then concave up is where the tangent lines are below, or the curve is above. All right, so one thing I want you to know is just kind of be able to look at it visually. So when I, think concave down, I want you to think about like a cup that opens down. So basically you're thinking about like the best one to think about for concave down is really just your full parabola that opens down. Like this is concave down. Now, any variation or portion of that, so you kind of see down below here, maybe I'm just talking about, this left half of it, that's still concave down. Not as maybe obvious when you first look at it because it's not the full kind of cup opening down look. And then maybe it's just the right half. But anything like this here, that is what it means to be concave down. Now, concave up then, think about a cup that opens up. So when you think about concave up, think about your parabola that opens up or any portion of it. Maybe it's just the right half, maybe it's just the left half, but you see it's like this cup that opens up. So you want to spend your time, a little bit of time familiarizing yourself with what you have here. Kind of looking at these visuals, hopefully it starts to make sense what concavity looks like. All right, now what we want to think about is, because we want to find these intervals of concavity, and we're really thinking about kind of the definition that I started with, and I was mentioning how where slopes are decreasing, that this is where f prime is decreasing, that is a definition. So where f prime is decreasing, that is another way to define where we are concave down. And where the slopes are increasing, so we think about where f prime is increasing, that is a definition then for where f is going to be concave up. All right, so what do I want to find? I want to find where f prime is increasing and where f prime is decreasing. That's what I want to find. So we already kind of know how to find where a function is increasing and decreasing. So think back to what we did with the first derivative test. So to find out where f is increasing or decreasing, we found where f prime, its derivative, was positive and negative. So think about, right? I mean, we did this a lot. This was your sign analysis, and you plug into f prime and you make conclusions about f, and where f prime is positive, you know f is increasing. Where f prime is negative, you know f is decreasing, right? We did that. Now what we want to do is we want to find where f prime is increasing or decreasing. So we need now where its derivative, so if I want to find now, instead of where f is increasing, decreasing, if I want to find where f prime is increasing, decreasing, then I'm going to need where its derivative, so f double prime, is positive or negative. So we just want to kind of extend that logic. So now we want to figure out where the second derivative is increasing, is positive or negative, because that is going to tell us where f prime is increasing and decreasing. All right, so pulling this kind of together here a little bit, and be careful, this was a screen capture I took from my digital copy of the book, but the primes didn't come through real well. This first one looks okay, this f prime, but this double prime looks really weird, so make sure you kind of fix that. And down below here. So again, this one right here. So where the second derivative on both of these, make sure you make those look significant enough. So let's kind of trace our logic back through here. So where the second derivative is positive, so we're right here. If the second derivative is positive, then that's going to mean that f prime is increasing. And going back up, f prime increasing, that is a definition for concave up. So if the second derivative is greater than 0, then f is going to be concave up on that interval. And so we're kind of pulling all of this logic here together, so we have this nice test that we can do for concavity. So the second part then, if we're thinking about where the second derivative, so where my second derivative is negative, that's going to be where f prime is decreasing. And if f prime is decreasing, that is our definition for concave down. So if the second derivative is negative, then the original function is concave down. So at the end of the day, this process is going to feel very similar to what we did last time with our first derivative test for determining increasing, decreasing, and local extrema. The difference is we're going to be doing all of this similar type of stuff. We're going to be doing it on the second derivative, and then we're going to be making conclusions about concavity. So that's sort of where we're headed. Now, where a function changes from increasing to decreasing, that's pretty obvious. Those are mins and maxes. Where a function is going to change concavity, these are going to be called inflection points. And so sometimes they might be more obvious, like maybe this first graph that I have here, it definitely starts, if we kind of think about this first graph, it's starting concave down, and then somewhere right about there, it changes to concave up. So yeah, there's very clearly an inflection point there. But then you get into the last two and they're a little more subtle. So you think about like the second one here, we are definitely concave up because if you were to draw in your tangent lines, they are below the curve. And then we change to concave down. Again, if you were to draw your tangent lines, they lie above the curve. And so these last two examples, the inflection points are maybe a little more subtle in their appearance. But places where a function is changing concavity is our definition of an inflection point. And we are going to find those inflection points, again, in a really similar way that we found extrema, but this time it's on, instead of the first derivative, we're going to be doing this on the second derivative. So inflection points, and again, please change this and make that double prime more significant for yourself there. So a inflection point, it occurs either where the second derivative is equal to 0 or the second derivative does not exist. Those are going to be our places where we will find inflection points. All right, so pulling all of this together, this is our steps, I guess I'll say, for finding concavity intervals and inflection points. So we start off, we have to first find the second derivative, and then we are going to look for where the second derivative is equal to 0 or where the second derivative does not exist. So these are our potential inflection points. So then what we do is we put these, kind of like before, we put these on our sign analysis. So let's say that we found a couple of values from up here where f prime was equal to 0 or didn't exist. So let's say we found those at some value at x equals a, and then a little further down the line, let's say we have another value at maybe b, at x equals b. All right, hang on, sorry, I need to put this on silent. Okay, so what are we going to do? Well, we're going to do something really similar as what we did before. The difference is, and this is where I think the labeling is really important, we're going to be subbing into the second derivative, and then we're still going to be making some conclusions about the original function. All right, so places where your second derivative, let's say we start off positive. Okay, so kind of going back to our line of logic up here, where the second derivative is greater than 0, that is where f prime is increasing, so f is concave up. So when the second derivative is greater than 0, this is going to be where f is, and we're just going to kind of show it like this, concave up. Where the second derivative, let's say we change to negative, that is going to mean that the original function is concave down. And so let's suppose, again, we just end with a positive in the second derivative, so going back to concave up. So those are our intervals of concavity. And then if we wanted to write out where the inflection points occur, those occur at the a, and whenever you need the y coordinate, it's always back to the original function. So a, f of a is an inflection point. So places where the function changes concavity is called an inflection point. Same thing down here. BF of B is an inflection point. All right, so that's going to be our process. Let's look at a couple of opening graphs, graphical examples. So here's one that is a logistic growth curve. You may recognize it from maybe science classes. You may recognize it from our era of coronavirus, where they're talking about trying to, slow down this rapid growth. And like right now in some areas, we're seeing it level off for a while before it turns back down to a decrease. So we've been able to kind of slow the growth of the coronavirus in areas, but in some areas it hasn't quite yet turned back to the decrease. So you may see graphs like this in the news as well. Okay, so just visually as you look at the graph, hopefully you can kind of see for yourself that we're starting off concave down. So maybe the book's definition is helpful, thinking about if you were to, attempt to draw in tangent lines in this first interval, the tangent lines lie below the curve. And so this is what we call concave up. So from here to here, this is where our function is concave up. And then kind of the second part of the graph, let's say, I'm sorry, I wanted to use red. It doesn't matter, but I'm trying to be consistent with the colors I used up above. Bear with me. So I'm going to draw this. I've been drawing in concave up above there in red, so I'm going to stick with it. All right, so this region, again, it is still concave up. So we start off the graph, and we are concave up. Now, if you look at kind of the second part of the graph, again, think about drawing in some tangent lines here, and I'm drawing mine in kind of dramatically, but they would definitely be lying above the curve. And I kind of just like to think of that like that cup opening up or the cup opening down idea as well. But this second part of the graph, this is where the graph would be concave down. Now, it's a little hard sometimes just to look visually, and sometimes if it's a graphical example, we may just have to estimate it. But this point right here that's highlighted as the point of maximum growth, this is our inflection point. And actually, the interpretation is really done for us on this one, and that's what they're saying right there when they say it is the point of maximum growth. So the inflection point is right here. Its interpretation is exactly that, when the growth is the max. Or you might say it as, maybe this, you could say it's when the function is increasing. It's definitely an increasing function throughout, and it's when it's increasing the fastest. So that would be kind of like another way that you could maybe think about that. So the growth after that point, so it was very rapid growth, that's the point of maximum growth, and then after that the growth rate starts to slow. And boy, do we hear that a lot in terms of the coronavirus, them trying to slow that growth rate. All right, so let's just look at another one. This one's not really in any particular context, but again, if we start off looking at the graph, I hope you can just kind of visually see it starts off concave up, right? It's a cup opening up. So if you like the idea of thinking about, as you would draw in your tangent lines here, these tangent lines would all, and those are not great looking tangent lines, but they would be below the curve here. So we definitely start off in a region that is concave up. And then we change over, if we look kind of at the second part of the graph here, again, if you were to draw in your tangent lines over here, those tangent lines would lie above the curve. And so this is where the graph would be concave down. And so there's definitely a point where we change concavity. And so it's always somewhat, especially here, we're not finding it by hand, it's going to be a little bit of an estimate. I'd say right about there, roughly. In this case, it is actually a point of horizontal tangency, FYI. But here is our inflection point. So this right here, and we're just kind of eyeballing it right now anyway, right? So this is our inflection point. And now to interpret that, if we were to think about this function, this is a decreasing function. And this is really when the function is decreasing the slowest. So we could say this might be when the function is decreasing the slowest. Or it could be the point of minimum decay. I don't know, something like that. So when the decline is the slowest. So it was declining kind of quickly, and then it sort of leveled out a bit, and then it starts, after that inflection point, then it starts to, then pick up that decline again. So this was really the point when it was declining the slowest. So there's a couple of examples of just identifying our inflection points and also interpreting those inflection points, which maybe isn't quite as obvious as interpreting extrema, just when it's the min or when it's the max is a little more obvious. All right, so in the next video, we'll come back and we'll find some of these values, inflection points, intervals of concavity. We will do some algebraically.